three possible places where these error sources will be developed. Okay, so according to this, we can have these three types of error sources. First is satellite dependent, that the errors are generating on the satellite itself. So the errors are originating from the satellite or are found to be part of the satellite transmitted signals or the information that has been provided in the navigation message. Okay, we will see a little bit in detail in further slides. So ephemeris, you understand this is the information about the orbit, satellite orbit and position. Okay, this is contained in the broadcast navigation message. So this information may be received wrongly, or wrong information may be received, or information as it is can be received about something that is happening, some disturbance happening in the orbit itself due to various forces or satellite geometry. Okay, satellite clock bias. So clock may be disturbed due to relativity effect or some clock drift is happening. Okay, we will see further about this. Then selective availability, this is intentional manipulation for national security reasons. This has been switched off. So this error is not anymore prevalent. Then observation medium dependent errors are there. That is, observation medium means the signal is propagating or traveling through the atmosphere. So the signal is encountering ionosphere and troposphere. These are the two parts of the atmosphere, and some error is induced through this propagation. That is, some delay is happening in the reception of the signal at the receiver. Okay, you can see in this figure, a satellite and receiver are shown, and this the range or the distance from the satellite to the receiver is known as range. The geometric range, that is the true range, that is the true distance, actual distance from the satellite to the receiver, is a small portion here, and some amount of delay or more distance has been traveled by the signal that it was supposed to. So all these errors show up in this way, and they are depicted in the pseudo range. So the various components of errors are there, as you can see in the table, and how much the error is they becomes prevalent in the range. You can see. So you can see largest amount of error that is coming in this signal delay is about 4 meters from the ionosphere. That is observation medium dependent error. So we will focus on this and discuss the different types of errors. The observation medium dependent errors originate during signal propagation from satellite to receiver, and station dependent and receiver dependent errors, they originate from the receiver, or they are present due to the location or vicinity situation on the ground about the station. Okay, if the station is placed in a congested area, so multipath and receiver and ACV, these kind of things will happen, or there is some obstruction happening during the propagation till the receiver, then cycle slips may happen. All those things, they are induced due to the vicinity situation. So we'll first discuss the first kind, that is errors originating on the satellites. So this is happening with the generation and broadcast of the signal. So we know that broadcast, ephemeris and clock information, all these things are contained in the navigation message. So this broadcast GPS clock and ephemeris information may contain significant errors relative to the true state of the satellite position and clock. So this information may be wrongly recorded, or the true state may be changing. So these two kind of scenarios can happen. So we can see some example scenarios in the table. For example, a clock fault may lead to sudden change in the timing of the broadcast signal while the position description remains accurate. So the position description is describing the true state, or the state that it was supposed to be in, but some fault has happened which was not recorded. So this is the first scenario. Second is the an unannounced maneuver where the orbit is suddenly changing due to various forces acting on the orbit, on the satellite. Okay, so and this is happening, but the clock remains accurate. Okay, so this will also produce erroneous information. Then satellite state may not itself change, but the navigation data that is broadcast to the user is changed to contain incorrect information. That is, recording is wrong here. Then everything about the satellite is correct. Either the user or the reference station incorrectly decodes the ephemeris information. That is, information has been passed correctly, but the decoding or the understanding of the information has been done wrongly. Okay, so these are some of the example scenarios how these errors can originate on the satellites. So such faults may appear as jumps, ramps, or higher order errors in GPS clocks, ephemeris, or both. Um, uh, these faults may be created by changes in the state of the satellite orbit, as we have discussed. So this is happening because many forces are acting on the predicted orbit. These forces may be gravitational or non-gravitational, tidal, etc. Okay, or simply we are getting erroneous information in the broadcast message. Then for GPS, nominal clock and position errors create projected pseudo-range errors that are typically have standard deviation better than 1 meters. Big faults are very rare due to this source of error. The use of single receiver operation propagates orbit error into the position results and causes amplification of positional error. So we are ultimately we are trying to find the position coordinates of the station receiver from all this operation. So in that positional error may be amplified due to these errors if these are not corrected. So differential positioning, that is DGPS, is an effective strategy for minimizing this effect. Second kind is the errors affecting signal at the receiver and vicinity. Okay. In the middle, we have that signal propagation error, which we will discuss later after this. So major errors caused by these kind or category of errors is multipath and APCV. So multipath depends on environment surrounding the antenna, and if the station is contained in a cluttered environment, it may experience multipath. Multipath means a reflection from reflective surfaces. So the signal travels a longer distance from the satellite to the antenna than the actual distance. Okay, this can be taken care by using carrier smoothing, which is smoothing the noisy pseudo-range measurements using precise carrier phase measurements. Okay, so multipath may result in cycle slips, which during processing are detected and repaired. Okay, so how do we treat multipath? We can select an observation site with no reflecting objects in the vicinity of the receiver antenna. There is a mechanism of making a choke ring antenna using a choke ring antenna, which is a device in the ground plane that has several concentric metal hoops. They attenuate the reflected signals. We can, under the same environment, the presence of multipath errors can be verified using a day-to-day correlation of the estimated residuals, because the satellite reflector antenna geometry repeats every sidereal day. Multipath errors in the undifferenced pseudo-range measurements can be identified if dual frequency observations are available. So we have the advantage of using dual frequency. It also helps in removing the ionospheric error. Multipath error is also reduced. Then there is a phenomena known as antenna phase center variation. So antenna is the place on the receiver where we are receiving the GPS signal from the satellite. So the signal is converted into energy, converted into electrical current. And if the antenna phase center, that is the point at which the GPS signals is received, does not coincide with the physical or geometrical center of that receiver itself, which it may vary due to elevation and azimuth variation of the GPS satellite and intensity of the observed signal. So if they vary, some error is induced. As you can see in this figure, that the geometrical center, that is the black dot, is different from the red dot. Red dot is the mean location of the center from the phase variation that is being received. So error magnitude depends on the antenna type, and it is typically of the order of few centimeters. This is difficult to model, so one should be careful while selecting the antenna type according to the application. So for short baselines, phase center error can be cancelled by differencing. By using same type of antennas and orienting all the antennas in the same direction, errors are highly correlated over distance. So differencing operation can reduce this type of error. Then for most practical application, this error can be neglected because it is very small size, rather very small size. So you can understand in the previous slides, we can see here it can be contained in the receiver noise or receiver and station dependent error. So that within 0.5 meters, this error is contained. So for practical application, we may neglect this kind of error. Now, main topic of the discussion is error due to GPS signal propagation. You are familiar with these two equations, these kind of equations. So these are two GPS observables, pseudo range and carrier phase. So you can recognize the terms written here. That rho term is the geometric range, then receiver clock error and satellite clock error, and then ionospheric, the circled ones you can see ionospheric delay depicted by capital I, then tropospheric delay depicted by capital T. Okay, so we have three codes. This CA code, then L1 and L2 frequency. So we have CA code and P code, these three equations we have for two different frequencies. So you can identify the terms, the delays contained in these pseudo range and carrier phase observables. Similarly, in the carrier phase equation, you can see this capital I term and capital T term. These are the delays from the signal propagation. So signal passes through ionosphere, that is 10 to 100 meters of delay it is causing, and neutral atmosphere. Neutral means electrically neutral portion of the atmosphere, that is there is no ionization or electric charges are present that are disturbing the signal. So this is rather smaller than the ionospheric delay, that is 2.3 to 30 meters of delay, depending upon the elevation angle of the satellite. So you are familiar with the elevation angle and azimuth angle. We'll be using these terms quite a lot in further slides. I hope I'm audible throughout. Is there any doubt up till now? Hello?
No, ma'am.
Okay, thank you. So to estimate an accurate position from range data, one needs to account for all these propagation effects and time offsets. These are the two types of equation sets for pseudo range as well as carrier phase observables. Now you can understand the structure of the atmosphere through these figures. So first on the left hand side, you can see the signal is first passing through the ionosphere, that is the light blue circle, and then through the troposphere, that is the dark blue circle over the Earth. So major portion of the error is induced from the ionosphere, and relatively smaller portion is induced from the troposphere. So you can see how the signal is refracted. You understand the phenomena of reflection, refraction. So reflection is when the signal goes away from after hitting a surface, and refraction is it is passing through the medium and changing its direction and speed. Okay. On the right hand side, you can see the atmospheric model where we start from the surface at the bottommost portion, that is troposphere. It is contained till a layer called tropopause. Then after that we have stratosphere, mesosphere, thermosphere, and exosphere. So above stratosphere, above mesosphere, we start to have active ionization happening, which may delay the signal in a different ways. So types of regions, that is the ionosphere is divided into are shown. So ionosphere is divided into sub-regions or layers according to electron density, which decreases as one gets further from the Earth. So electron density is decreasing as we are getting further from the Earth's surface. So these are named as D, E, and F region. F region is further divided into two other regions we will see in further slides. Okay. So let's discuss troposphere. The lowest portion of the Earth's atmosphere is the troposphere. You can see in the figure. So up to 10 kilometer is the tropopause. That is the distinction between troposphere and the ionosphere. 80% of the atmospheric mass and 99% of its water vapor is found in the troposphere. Rest is very rare as we go upwards. So we have a trend in temperature that temperature generally decreases with the altitude at a constant lapse rate. Lapse rate means deceleration or negative, what you'll say, negative trend as we go with the altitude. So constantly it decreases about from -7 to -5 Kelvin per kilometer of altitude. You can see this trend. Because of this trend in temperature, we have different portions in the atmosphere. Okay, so the layer up is the stratosphere followed by mesosphere. Distinction between the layers is made with the vertical temperature lapse rate. So wherever the lapse rate changes, we have a different portion of the atmosphere. So whether it's happening inside the troposphere, temperature is you can see temperature is about 20 to -40 degrees centigrade. Then clouds are found in this region, and this region is electrically neutral and non-dispersive medium for radio frequency below 15 gigahertz. So for GPS signal, that is frequency of L1 and L2, if we understand, it is about 1.5 to 1.5 gigahertz and 1.2 gigahertz. Okay, so for below 15 gigahertz, this portion of the atmosphere, that is troposphere, it is non-dispersive medium, means the signal is not being divided. It is not it's not dispersing while traveling through this medium. Okay, so having a dual frequency does not help us in removing the error or signal delay caused inside the troposphere. Having a dual frequency system of GPS may aid us in removing the ionospheric error because there that is dispersive medium. But for frequencies below 15 gigahertz, that is where the GPS signals are concerned, non-dispersion is happening in this medium. So the signal is radio band. GPS signal is radio band that is contained inside the electromagnetic spectrum, okay, microwave region. So we have to understand the propagation basics as electromagnetic wave propagation. That is originates from Maxwell equations that is contained in the red box on the right hand side. Four sets of equations. They show how electric and magnetic fields are generated and altered by each other, like how the magnetic field is changing electric field and how the electric field is changing the magnetic field, while they propagate through a medium where charges and currents may be influencing them. Okay, so this kind of propagation is understood from these set of equations known as Maxwell equations. So in these set of equation, you can see capital E and capital H are electric and magnetic field vectors. Capital D and B are electric and magnetic flux densities. Mu and epsilon, these are two important parameters here. Permittivity epsilon and permeability is mu. These are related to the electric and magnetic susceptibility of the material. So the material that is through which the signal is propagating, these are described by these two parameters, epsilon and mu. And while doing some manipulation from the Maxwell equations, for example, for troposphere, we can put some parameters 0. For it is isotropic, non-conducting and neutral medium. So we can put some parameters 0 in these equations to get or to derive the wave equations. Now the wave equations are relating or bringing in the concept of refractivity index. So you understand how the signal was getting refracted while traveling through the ionosphere and the troposphere. Here you have seen. So this refraction itself tells us there is a concept of refractivity index, that is small n, you are familiar with. So we have to relate this n with the propagation. So this is done through wave equations which introduce the refractivity index at any given location along the wave path, and we can derive the propagation characteristics. Focusing on delay, we are interested in delay, how much delay the signal is getting affected, and how much dampening of the electromagnetic wave is happening. Dampening means how much absorption is happening while this refraction is happening. Okay. So from the previous slide, the most important portion is the refractivity index. So from refractivity index information, we will derive what would be the length that has been traversed from the satellite to receiver. Okay. So atmospheric refraction of the EM wave, that is electromagnetic wave, is represented by refractive index N or refractivity N. So refractivity is just a term, as you can see on the right hand side, the equation is given. Capital N is the refractivity. This is just for our convenience that we have introduced this parameter N, so that we can understand different values of refractivity different from unity, that is 1. So if the numbers are very close to 1, like 0.00 something, very close to each other, then it is difficult to make a distinction between them. So to avoid that, we are introducing a term called refractivity. So it avoids the usage of numbers that distinguish only very little from unity. Since refractive index N is a complex number, so we will have two types of two portions of refractivity, the real part and the imaginary part. So this is depicted on the equation on the right hand side. You can see first portion, first two terms are contained in the real part, and the last portion is contained in the imaginary part. So real part is responsible for the refraction and the delay happening during the signal propagation, while the imaginary part is responsible for the attenuation or absorption. So attenuation means any disturbance on the signal, and absorption, while it is getting absorbed, so it is getting useless for us. So how much the signal is damping, how much is the attenuation or absorption will be obtained from the imaginary part of the refractivity. Um, So for main air constituents like the dry gases and water vapor, etc., the mixing ratio of the constituents is constant. How much mixing, the proportion in the mixture of the atmosphere, that is known as mixing ratio, and it remains constant. So the refractivity of a packet of air at a specific pressure and temperature can be identified. But for water vapor, that is our main interest area here, water vapor has a very variable mixing ratio. Like in some places, it would be drier than other places, or some places may be more humid than other places. So very variable mixing ratio, and its refractivity also depends on density or temperature due to dipole moment. So you can see in the figure there is a constant permanent dipole moment of water. We have a large molecule of oxygen and very small two molecules of hydrogen, giving us a dipole moment, negative and positive charge. So this significant dipole moment can influence the propagation of electromagnetic waves. So they can influence how much delay can happen inside the troposphere. I hope this much part is clear. So we are just introducing the term refractivity. What are the different two parts, that is real part and imaginary part, and how the dipole moment of water is influencing the propagation of electromagnetic waves. So since water is the mixing ratio is different and how it affects the signal is different, wet and dry constituents of the atmosphere will affect the propagation delay in different ways. Okay, the dry portion will be affecting in different way than the wet portion. Spatial and temporal distribution of water vapor is very variable. So dry atmosphere constituents are only varying little over temporal and spatial scales. So the drier constituents are more stable and constant behavior, while the wet, that is water vapor, is very variable. So hence there are two different effects of refraction. Thus propagation effects exerted from the dry air part can be well modeled. Okay, we can understand what is the pattern for a region, for a place, and we can model using empirical constants. Okay, so we can easily use empirical models to get the value for propagation delay for the dry air part. Okay, but it is difficult to understand how wet constituent is changing at a place or with time. Okay, it is highly variable. So these empirical models are not very successful to model the wet part. The refractivity model of the atmosphere can be written as the sum of three main constituents. So you can see the equation below on the left hand side. Capital N, that is total refractivity. By refractivity, you understand it is the characteristic of the atmosphere, or mainly the troposphere, how it is changing the direction and speed of the signal while it is traveling from satellite to the receiver. Okay, so total refractivity is divided into three portions. First portion, that is the dry air part. Due to the dry air part, dry term is also synonymous with hydrostatic. Okay, hydrostatic, that is water characteristics are very static over there, and non-hydrostatic, that is the wet part. Okay, so capital N small h represents the hydrostatic refractivity. Then the middle portion is due to the density variation of the water vapor. Then the third portion, the last portion, is due to the dipole component of the water vapor. Then if we combine the middle and the last portion, we get the wet refractivity. It is a very important term, or also known as non-hydrostatic refractivity. Okay, so ultimately we are dividing the total refractivity into two portions: hydrostatic refractivity and wet refractivity. Hydrostatic refractivity and non-hydrostatic refractivity. One due to the dry air components and the other due to the wet component. Wet component is water vapor. Okay. So hydrostatic refractivity depends only on the total density of the air, which can be easily understood or measured from the ground-based pressure measurements. While the wet part is related to the temperature and water vapor pressure. So temperature, vapor pressure, all these things have to be known, which are very difficult to understand the variation of water vapor in a region. So density rho is the density of the air parcel including the water vapor. So rho used on the right hand side equation is the density of the air parcel, total air parcel with the wet and dry components. It is included in the hydrostatic refractivity portion. That is the first portion of the equation, K1 R upon MD rho. And for the wet part, we have vapor pressure PW, temperature T, K2 and K3 are empirical constants, and ZW is the compressibility. It represents how much the deviation is occurring from the ideal gas law. Okay, so this constitutes our equation for the refractivity, total refractivity. It has two portions: wet refractivity and dry refractivity. In other terms, we call it hydrostatic refractivity for dry part and non-hydrostatic refractivity for the wet part. I hope I am clear up till now.
Yes, ma'am.
Okay. So we are talking about the error caused by the propagation of the signal. So how this error is propping up? It is popping up into the delay measurement. What is delay? The signal is coming from the satellite to the receiver, but it is getting delayed. It should arrive earlier than what time it has arrived. Okay, since it is arriving at the receiver a little bit late, that means it has traveled a little bit more distance than it was supposed to. Okay, so that little bit more distance is represented by tropospheric delay or ionospheric delay or atmospheric delay. Okay, so since we are we are studying the troposphere right now, we are understanding the propagation delay caused by the troposphere. Okay, so electric path length capital L can be expressed as shown by the right hand side equation. First equation, L equals to integral of refractivity index N, which is a function of small s, that is the distance along the ray path, along the signal path. Okay, infinitesimally small distance ds, okay, is the distance that is happening along the true ray path from the satellite to the receiver. So satellite is capital T, receiver is capital R. The integral is happening from the satellite to the receiver. You can understand this equation very easy. So it is the product of refractive index and the distance traveled. Okay, so this is the electric path length. Now what is happening for vacuum? Refractivity index is 1. So we arrive at a straight ray path. That is, if there was vacuum, there was no atmospheric medium between the satellite and the receiver, the signal would have gone through like a razor. No delay, nothing happening, no disturbance happening. So that straight ray path is known as the geometric distance, capital G. Okay. So what is delay? That undisturbed ray path minus the disturbed ray path, that is the longer distance, minus the undisturbed ray path, that is geometric distance, capital G. So you can see in the second equation, that is delta L, that is the tropospheric delay. That means it is the difference between these two path lengths. That is the first path length, that is electric path length, capital L, minus capital G. What is capital G? If there was no atmosphere, small n, that is refractive index, was 1. If there was vacuum between the satellite and receiver, there would be no disturbance, no delay. Then the actual geometric distance between the satellite and receiver would be capital G. So the difference between the true distance traveled by the signal because of the atmosphere minus the actual distance, geometric distance, this is known as capital L, that is tropospheric delay. Okay. So if you substitute the refractivity inside this small n, that is refractive index, we arrive at an equation that is represented in the third equation. So delta L equals to, what was refractivity? If you remember from this equation, capital N equals to n minus 1 into 10 to the power 6. So in place of small n, we are substituting capital N into 10 to the power minus 6 plus 1. Okay. Here when you substitute this, you will get an integral from R to T, integral of ds. That is small distance along the two ray path. This has been integrated from distance of receiver to the satellite. This is known as capital S, and this is the geometric length of the true propagation path. Okay. So since that plus 1 has come inside this equation, that plus 1 will give us this integral from R to T ds, and this will result in capital S. So you understand how this capital S is coming. So we can estimate tropospheric parameters when assuming a relation between zenith tropospheric delays and those observed at arbitrary elevation and azimuth angles. We'll see about this point later in this later slides. What is zenith and what is in different directions, what are the delays. Okay. So you understand the wet and dry components of the tropospheric delay is due to that refractivity capital N here in the first red box. Okay, the capital N refractivity, as we have seen in the previous slide, is divided into two portions, wet and dry portions. Because of that, we have tropospheric delay in two portions, that is wet and dry components. Okay, the smaller red box on the red side shows us what is the bending effect, how much the ray has bended while it has propagated through a medium. Through a which medium? Through troposphere. Okay. So because of refraction happening, there is some bending, and how much bending effect is there? It has been captured from this capital S minus G. Okay. So what is the relation between this delay and the elevation angle? Tropospheric delays increase with decreasing satellite elevation angle. So you understand what is elevation angle of a satellite? How much the satellite is making an angle from the horizon. Okay, as it is traveling up the horizon towards the zenith. Okay, I'm sure you are familiar with these terms. What is zenith? Zenith is the point directly above the observer. Okay, 90 degrees. So from the horizon, that is 0 degrees, like point in front of the observer straight at the end, that is horizon. From horizon towards zenith, when the satellite travels, we get some elevation angle. Okay, so tropospheric delays increase with the decreasing satellite elevation angle. So the closer the satellite towards the horizon, we will have lower and lower elevation angle. So you can see in the right figure, top figure, we have two portions of delays. First is the straight portion. If when the satellite is at the zenith, there is, how much is the elevation angle? 90 degrees. Okay, so that is very smaller portion of distance traveled inside the troposphere as compared to longer inclined distance, as you can see when the satellite is at a low elevation angle and more towards the horizon. Okay, so path affected by tropospheric refraction is more when there is an angle or inclined distance, and if the path is straight towards the zenith, it would be lesser. So hence tropospheric delays increase with decreasing satellite elevation angle. This increase in delay as a function of elevation angle, it should be understand, or it should be accounted for, and this can be done by using a mapping function. So what is a mapping function? It is this hz, that is the height of the point where the ray is leaving the atmosphere, okay, in this inclined distance, upon the slant delay, capital R. How much is the delay? Okay, this is sine epsilon. So mapping function would be 1 upon sine epsilon. What is epsilon? Epsilon is the, here epsilon is the elevation angle. So many slant delays at a given time can give rise to many unknowns. So there are so many directions from 0 degree to 90 degrees. Okay, so there can be many slant delays. The signal can travel at any elevation angle, so many unknowns will be arrived at. So to avoid this, for a flat homogeneous atmosphere, we can reduce the number of unknowns by projecting all the slant delays onto the zenith direction, which leads to a one single zenith delay. So you can understand there can be only one zenith delay, that is straight portion, is straight or vertically up portion, and there can be numerous inclined distances, inclined delay, that is slant delays. So to avoid a large number of unknowns, we can project all these slant delays to vertically up direction, that is zenith delay. Okay, so you understand what is zenith delay, I hope. Zenith delay is determined by the integration of refractivity vertically. So how we are obtaining the delay, propagation delay in the troposphere? We are integrating refractivity into distance. Okay, when the distance is not slant, when the distance is vertical, then we will get the zenith delay. As you can see the equations written on the right hand side, we are using the term Z instead of small s. Okay, this Z means vertical distance. Okay, so in this flowchart you can see the total atmospheric delay can be divided into two whole parts. The bigger one is the ionospheric delay. The delay is typically up to 10 meters, and the relatively smaller portion is the neutral delay, that is tropospheric delay. Again, tropospheric delay can be divided into two parts. Because refractivity is divided into two parts, we have two types of, or two portions of delay, that is dry or hydrostatic delay, wet or non-hydrostatic delay. Okay, so major portion is the dry part, because water vapor is present in little amount than the other portions. We have more of the dry delay and less of the wet delay. Zenith hydrostatic delay, zenith wet delay. Okay, Now, hydrostatic delay depends on three characters, that is pressure, temperature, and refractive index. And wet delay depends on water vapor. Atmosphere is very close to hydrostatic equilibrium. This is a phenomenon in physics, which means that surface pressure is given by the vertical integration of the density. Okay, so the first term in the refractivity depends only on density, as we have seen. If I go back to the slide, the first term on the right hand side equation, we have that rho. That rho symbol tells us the total density of the air parcel. Total means dry plus wet. Okay, so since the first portion only depends on the density, its vertical integration will depend only on surface pressure because of the hydrostatic equilibrium phenomena. Okay, so ZHD, that is integral, vertical integral zenith hydrostatic delay, and integral of the wet part of the refractivity will be represented by the zenith wet delay. Vertical integration needs to be carried out from height h0 to upper height of the atmosphere, h infinity. So these two heights are represented in the equation on the right hand side. h0 is height near the Earth's surface and h infinity is the top of the atmosphere. What is zenith hydrostatic delay? We will see a little bit in detail. ZHD. So zenith delay is vertically up direction, the delay in the vertically up direction where the observer is standing. Okay. So almost all empirical models that are able to model tropospheric delays for the analysis of the GNSS data require the user to input pressure values at the locations where the observations have been taken. Meaning we need only pressure values in order to understand or model the hydrostatic delay portion or the dry delay portion. I'll again repeat, we have two portions of refractivity, total refractivity, that is wet refractivity and dry refractivity. The refractivity is contained in the delay equation, hence we have two types of delay, the dry delay and wet delay. So what is the ZHD? ZHD is the zenith dry delay. Okay, dry delay that is happening in the zenith direction. What is zenith direction? Point directly above the observer. Okay, for modeling hydrostatic delay or dry delay, we only require pressure values at the location where the observations have been made. Okay, why do we need only pressure values to model ZHD? Because of the phenomena known as hydrostatic equilibrium. You can see on the right hand side, hydrostatic equilibrium of the atmosphere is depicted by this equation: del P by del Z plus rho function of Z, G function of Z equals to 0. Here small p represents pressure, Z represents height or altitude, rho represents the density of the air parcel, G represents the gravity. Okay, so we have four terms here: pressure, height, density and gravity in the hydrostatic equilibrium. So if Gz is the total gravity acceleration and Pz is the density of the air, both are functions of altitude, that is height, Z. Integrating vertically provides us with pressure value P0 at a given geopotential height H0. Okay, so how do we arrive at P0? We integrate the second portion of the equation from height H0 to infinity. Infinity means top of the atmosphere. Okay, so we will get effective gravity GF and integral of water vapor density and height, vertical height, that is altitude. Okay, because of this we only need pressure value to arrive at the water vapor density or hydrostatic delay. Okay, Since hydrostatic delays are solely dependent on pressure, one can derive an accurate model for this part of the atmospheric delay quite easily. So dry delay easier to model, wet delay difficult to model. Why dry delay is easier to model? Because we only need pressure values at the location and location information. Where is this location? We also need that data. That is, we need latitude of the site and geopotential height of the receiver. Okay, we input these two values in the SASTM 1N hydrostatic delay model. This is one of the empirical model that we are talking of. You can see the equations below. ZHD is given by this, where G effective value is function of latitude and height. As we have seen, gravity as a function of height. And some coefficient K or kappa, which is a function of phi h naught, the value is given. It is function of again latitude of the place and geopotential height of the receiver. So using these information, that is the location of the height, location means the latitude of the site as well as the height of the receiver, as well as pressure values, we can compute or model the zenith hydrostatic delay, that is ZHD. I hope I'm clear. Let's take a break of 5 minutes. If you have any questions up till now, just let me know. If you want me to go to some previous slide, if you have some doubt, I can do that also. I'll slowly show you the slides to refresh your memory. If you have any doubts, just please ask. Okay, I can see there are no questions. You can go ahead and please just ask any query if you have in mind. So there are a few key points up till now. We have divided errors into three portions. First, errors generating at the satellite, then errors happening during the propagation or travel of the signal in between the satellite and the receiver, and the third category is the errors happening at the receiver. Then focusing on the error due to signal propagation, we have propagation delay happening due to two portions of the atmosphere. First is ionospheric delay, that is a little bit larger value than the second type, that is tropospheric delay, that is neutral delay. Okay. Now, delay or the signal can traverse through the atmosphere at different elevation angles. So, when the elevation angle is 90 degrees, we have zenith delay. And when the elevation angle is between 90 degrees and 0 degrees, that is at some particular elevation angle of the satellite, then it is known as slant delay. Okay. So to reduce a lot of unknowns, that is slant delays, we project all of them into the zenith direction, that is vertically up direction, to compute the zenith delay. Now, delay is of two types, wet delay and dry delay. That is hydrostatic delay, that is ZHD, which is also known as dry delay, and wet delay, that is zenith WD, ZWD, or zenith wet delay. Okay, we have seen how it is easier to model the dry part or the hydrostatic delay or the ZHD because we need only the location information and pressure during the observation. Okay. So one of the models that we will discuss later on is the Sasta-Moine model to model the ZHD. It is empirical model using pressure values. Okay.
Ma'am? Ma'am?
Yes, tell me.
Ma'am, what causes the zenith delay?
Zenith delay is when you can imagine a scenario that you are standing at Earth's surface, okay, and the satellite is directly above you, and
Yes.
the signal is received into your phone if your phone is the receiver. Okay, so that that vertical distance that the signal is traveling from the satellite to your phone is the zenith delay. Okay, you can see in this slide, if you
Ma'am,
are standing at
I'm
a portion,
asking what causes this?
what causes this? I told you, no? It is caused due to atmospheric refraction. Okay.
Ma'am, but when the that signals are following the normal path, then I think refraction will be least.
Least, yes, that is what I'm saying. You can, in this slide, you can see the first line, what is written. Tropospheric delays increase with decreasing satellite elevation angle. So highest elevation angle is 90 degree. That is this vertical line. Okay.
Yes, ma'am.
Highest elevation angle means least delay. So you can see the length of that line. It is smaller than the inclined line.
Okay, ma'am.
Okay. Understood?
Yes, ma'am.
Okay, I'll move. Sorry. Yeah. So next, naturally, is the wet part. That is zenith wet delay. Okay. So water vapor delay, that is the second term in the refractivity, which corresponds to the second term in that refractivity equation. It is not so easily integrated. Why? Because there is highly varied distribution of water vapor with height. At some point, it would be some value at higher altitude, it would be some value. So very quickly it changes the amount of or distribution of water vapor. So surface measurements that we can do, since we are standing on the Earth's surface, we can only measure water vapor pressure at the surface. Okay, but these measurements are not very effective because it can be dry at the surface and moist above, or it can be moist or humid at the surface and dry above. Okay, so the surface measurements, they don't give a very accurate picture of water vapor. So there are few effective methods, for example, using water vapor radiometer or LiDAR, but these effective methods are very expensive. So what is the alternate efficient effective method alternative we are given with? That is measuring the zenith wet delay. Zenith wet delay we are measuring from the GPS. It is relatively and cost effective technology. Okay, you have GPS on your phone. Okay, so since surface measurements are not very effective and other effective methods are expensive, we are left with our only option, that is GPS. So empirical models for wet delay prediction rely solely on surface or site dependent data. As we have seen, while modeling the ZHD, we were using? We were using pressure and the location of the site. These two things are the characteristics at the site. Okay, these are the measurements of the site or of that particular region, of that particular surface. So empirical models, they use that information. They rely only on that. So again, these models will not be able to model the wet delay prediction very nicely. Okay, such model will give reasonable estimates of ZWD for standard meteorologic conditions. What are standard conditions? For example, there is no rain event. Okay, normal conditions, normal sunny days happening, and there is not much change in weather. Okay, all these things are standard meteorologic conditions. Okay, so they may give some reasonable estimates of ZWD, but they fail to predict these ZWDs with centimeter accuracy for weather situations that deviate from such an assumption. What is the assumption here? Standard meteorologic conditions during which these empirical models might work. But if the weather is changing very fast or the weather is changing in very extreme pattern, then these predictions do not work. So in meteorology, the term precipitable water is used. What is precipitable water? In the figure on the right hand side, you can see the Earth's surface, and you can see that that test tube is kept on the Earth's surface, and the clouds are precipitating water inside the test tube. Okay, so how much is that water collected in the units of distance is known as precipitable water. So the cross section of that area or the test tube or the column is fixed, and we arrive at precipitable water vapor. So PWV, from ZWD we will arrive at PWV. What is PWV? You can always remember this picture on the right hand side. The water collected in the constant area tube is known as PWV. When you measure the height of water that has been collected, just like rain gauge. Okay, so this is the integral of water vapor density with height and equals the depth of water if all the water vapor precipitated as rain. Okay, if the mean temperature of the atmosphere is known, PWV can be related to zenith wet delay. What was zenith wet delay? Portion of zenith delay. Okay, wet portion of zenith delay. Now from wet portion of zenith delay, that is ZWD, we are arriving at precipitable water vapor. So you understand these terms. From delay, we are arriving at zenith delay. From zenith delay, we are arriving at zenith wet delay. From zenith wet delay, we are arriving at precipitable water vapor. Okay. So precipitable water vapor, if we include the information of mean temperature of atmosphere contained in this factor pi. You can see in the equation written below. And multiply this factor to ZWD, we will arrive at PWV. PWV means precipitable water vapor. Now mapping function I've already discussed with you. What is mapping function? The dependence of the delay with the elevation angle of the satellite. Okay. Low elevation angle, larger delay. Less elevation, more elevation angle, then smaller delay. So this relation is contained inside the mapping function. One needs to have a mathematical approach that relates between the delay in the zenith direction and one observed at a given elevation angle. This can be done through a mapping function. In the simplest form for a plane atmosphere, elevation angle dependence would have been 1 by sine epsilon, if you remember. The first the equation here, mapping function equals to 1 by sine epsilon. Okay, this is the simplest equation for the mapping function when their very basic assumptions have been made. What are those assumptions? It is assumed that spherical constant height surfaces could be approximated as planar surfaces. The Earth is round, so the directions would be affected as taken from planar surfaces. Okay, so this approximation will act as accurate information only for high elevation angles. What is high elevation angle? Towards the zenith. Okay, higher elevation at zenith, the elevation angle is 90 degrees. Okay, so when the elevation angle is more and more towards 90 degrees, towards vertically up towards the zenith, then the amount of bending or the effect of bending decreases. You understand when you like throw some light from a torch into a bucket of water with vertical direction, then that there is no amount of bending happening or very small degree of bending happening, bending of the light. And when you throw the light from the torch with some inclination inside the water, then the water inside the water, the light will bend. Okay, more inclination, more bending. So you understand, the more higher elevation angle, there would be small degree of bending, and for low elevation angle, then there will be for low elevation angle, there will be higher degree of bending. Okay. If you have any confusion, yes, tell me.
We are calculating that angle from horizontal, isn't it, ma'am?
Yes, sir. Yeah.
Okay.
Yeah. So from horizontal means from horizon. At horizon, you understand what is horizon? The
Yes,
sun, when the sun sets, it meets the horizon. Okay. So from horizon, the elevation angle is 0. And when the sun is on the top of your head, that is the zenith direction, that is set. And if you understand the sun as a satellite, you understand that the elevation angle is maximum at the zenith. For a spherically symmetric atmosphere, spherically symmetric means curvature effects we are ignoring. Okay, then 1 by sine elevation mapping function will work. But since there is there are curvature effects, we have to use the continued fraction representations. So the direction is continuously changing because the earth is not have the surface is not the planar surface. Okay, that is why there would be continued fraction inside the mapping function. This is represented in the second equation, you can see. So this is a little bit more accurate version of the mapping function. The most high approximated form of the mapping function is the topmost equation. Then second one is higher accurate approximation. Then what we can do is this will go on, that continued fraction will go on to infinity, infinite times. So we can truncate this form. Okay. We can introduce some coefficients dependent on specific weather conditions, and they are also function of the latitude of the region. Okay, so location information and that region specific weather conditions. These two factors influence the coefficients inside the mapping function. In the third equation, you can see A, B, C. Okay. So these equation, and you can also notice that small I that is written, that represents for both. We have two types of delays, hydrostatic and wet. Okay. So different mapping function for each type of delay. For wet, we have wet mapping function. For dry, we have dry mapping function. So that is represented by small I there in the third equation. Okay. Small e represents the elevation angle, and ABC are the coefficients dependent on weather conditions and latitude of the region. Okay. So there are different parameterizations used for mapping function. When you use a GPS software, for example, Gamut or Bernice, you choose what mapping function you are going to use, converting the slant delays to the zenith delays. Okay, so which type of function you are going to use, you have to choose inside the software. Okay, so some options are Neal mapping function, which is very popular, where ABC are latitude, height, and day of the year dependent. What is DOY? Day of the year. So time of the year, which what time? Because time carries the weather information. At what time of the year, what weather would be prevalent over there. Okay, latitude and height are the location information. So these informations, these info are required for Neal mapping function. And another popular and more accurate mapping function is Vienna mapping function. This uses ray tracing. Ray tracing means the signal ray from satellite to a receiver is being traced. Which path it is taking, we are tracing it exactly through 3D atmospheric model. Okay. While tracing the signal path, we can calculate the accurate mapping function every 6 hours on the global grid. So this is a global grid, Vienna mapping function. This is calculated for every region of the earth. Okay. So the last equation you can see, that is slant total delay, can be written as mapping function into ZHT plus mapping function into ZWD. Okay. Total is given by dry plus wet. Okay, and slant is given by multiplying mapping function to the zenith one. I hope you understand. There are two types of mapping function also, because there are two types of delay, dry and wet. I hope you understand the last equation. Slant total delay is given by slant hydrostatic delay plus slant wet delay. How slant hydrostatic delay is written? Zenith hydrostatic delay ZHT into mapping function for the dry portion, MH. Then slant wet delay is written as multiplying wet mapping function with the zenith wet delay. I hope this is simple enough. Now we come to gradients. So you can see in this figure what is elevation angle. It is very nicely shown. Directly in front of the observer is the horizon. At horizon, when that what is called hypotenuse, when the hypotenuse is meeting that base, it is 0 degrees at the horizon. When it rises from the horizon, the elevation angle is increasing from 0 to 90 degrees. Okay. Now that variation in angle, how the satellite rises above the horizon, is known as elevation angle. And what is azimuth angle? In which direction into 360-degree circle around the observer you are observing. Okay, so you can see azimuth angle, it is computed from north. Okay, so front and up direction will make you understand the elevation angle, while north, south, east, west will make you understand the azimuth direction. I hope you don't confuse these two angles. So when we are studying the mapping function, what is mapping function? We are using the slant delay and we are converting it into zenith width delay. Okay, zenith delay using elevation angle. Okay, so this is known as mapping function. They assume that everything is stable and constant in all the azimuth directions. Okay, north, south, east, west, everywhere this is the same situation happening. So this is known as azimuthal symmetric atmosphere around the GNSS slide. So anywhere you turn around in any direction while observing the satellite, this is known as azimuth direction, 360 degrees. Okay, so while obtaining the mapping functions, we work under the assumption of azimuthal symmetric atmosphere around the GNSS site. But due to local and regional climate and weather conditions, atmospheric delays at constant elevation angle will slightly vary with the azimuth direction. Okay, so there is variation in the elevation direction, and again there is variation in the azimuth direction. What variation? Variation in the water vapor information. Okay, how water vapor is changing? It is changing from front to up. It is changing from north, south, east, west. Okay, so in order to account for such an effect, the so-called gradients need to be estimated together with the wet tropospheric delays for utmost high precise positioning application. So what are the terms that take care of this azimuth instability or azimuth variation in the delay information? We have gradients. So the gradient mapping function considers elevation dependency having the two horizontal gradients. So for simplicity, we are considering in two directions, north, south and east, west. Okay. So two horizontal gradients we are introducing, that is GN and GE. They are estimated together with the zenith delay during GNSS data processing happening in the GNSS software, that is, for example, Gamut and Bernice. Okay, so we use a model given by Chen and Herring, which is shown. The equation for that model is shown below. So MGR represent gradient mapping function, which is a function of both elevation and azimuth angles. Okay, mapping function is only function of elevation angle. Now gradient mapping function is function of azimuth and elevation angle. Okay, so these are estimated together with zenith delay information during GNSS data processing. What do we do during GNSS data processing? We try to obtain accurate position of the station. Okay. Now, during this main process, we obtain some errors. कि कहाँ errors आई हैं. So one of the error component is delay that is happening due to the propagation inside the atmosphere. Okay. So along with that delay error, we are also understanding what is the gradients in the azimuth, what is the error in the azimuth direction. Okay, so these two things are estimated together during GNSS data processing as byproducts apart from the main process of obtaining the accurate position requirement, position of the station coordinate. Okay, I hope this is clear. What are gradients? What is mapping function? I hope this is clear. So mapping function you always associate with elevation. and gradients you associate with azimuth. How do we treat tropospheric delay? We can ignore it completely, okay, but we have to take care that we are not using very low elevation satellite information, okay. If we are going to ignore tropospheric delay, we have to consider higher elevation angle data, because for higher elevation the delay is very less. Okay, so generally no observations are taken below 20 degrees of elevation. We can correct the data using standard tropospheric refraction model. As we have discussed, the name of one of such models like Sastamoinen model. Another model we will see in further slides, that is Hopfield model. These two are popular models. So we can use an empirical model to model these and remove them from the positioning estimate. Okay, so this is with or without surface meteorological readings. What are meteorological readings? Temperature, pressure, and relative humidity. These three things are the meteorological information. Okay. These models predict the dry part delay to 1 centimeter and wet part delay to 5 centimeters. You can see how well they are predicting the dry part with error as low as 1 centimeter, and the error in the wet part is up to 5 centimeter. So wet part is relatively difficult to model using these empirical models. So another is estimating residual tropospheric effect as an additional parameter. Okay, additional parameter as additional to the positioning estimate. So this is a very high precision work. So high precision means more cost involved. Another is difference the data between sites. So more correlation will be present over short to medium baselines. So effect of this error will be minimized if we use differencing. The more efficient treatment of tropospheric delay would be measuring the wet path component directly. So how to measure? We can use a instrument known as water vapor radiometer, but this is also very expensive, so hence it is not a viable option. But this gives us the direct information how much wet propagation delay has happened.
Ma'am,
Yes.
ma'am, like in first point that we avoid taking below 20 degree. Ma'am,
Yeah.
there is one question that maybe it will be silly, ma'am. How we can know that that satellite position is below 20 or at any angle? How do we come to know about this?
This is obtained in the navigation message. No, what is the elevation angle? What is we have Rhinex files you are familiar with.
Yes, ma'am.
So
Yes,
we
ma'am.
have O file, M file, N file, if you remember. So N
Yes, ma'am.
file is navigation file. So in the
Yes.
navigation message, we generally get what is the position of the satellite, what orbit, and all those information is contained in that. Also for
Okay.
IGS station, we have that information from the IGS website. Okay, so that is easily available. I hope the doubt is clear. I'll
Yes,
move
ma'am.
on.
Thank you.
Okay. So the empirical models that we were talking of, for example, one we have already seen Sasta Moanin. We will see it in detail a little bit in next slides. So Hopfield model is one such empirical model to which gives the dry part with more accuracy and wet part with lesser accuracy. Okay, so this is based upon a large number of meteorological radiosonde balloon profiles made at various geographical locations over a number of years. So we are using huge amounts of data collected about the meteorological parameters from atmospheric sounding done by sending up balloons, weather balloons inside the atmosphere. Okay, to which an instrument known as radiosonde is attached, and it measures the pressure, temperature, and relative humidity at different levels, at different intervals of time. Okay, so this is done twice a day every day at those radio zone stations. And the Hopfield model and such models are based on the large number of readings collected by these instruments. Okay. So it incorporates altitude variation of atmospheric refractive index based on refractivity at the surface and characteristic height. So we are using refractivity at the surface. That information is being used, plus some characteristic height is being introduced. What is this characteristic height? Up to what height is the wet delay or the dry delay is uh, influencing our signal? Okay, that is the characteristic height. It is a hypothetical height above which the refraction effect could be neglected as far as propagation delay is concerned. Okay, so in the figure on the right hand side, you can see there are two types of height. Two circles, circular arcs are there at different heights above the surface of the earth. You can see. So HW is the wet characteristic height and HD is the dry characteristic height. Okay, so these two characteristic heights are obtained from the Hopfield model. So this model gives expressions for effective heights of the troposphere with respect to both dry and wet components of the tropospheric delay in a quartic model. Quartic is just polynomial, which degree of polynomial is being used. Okay. The equations written below corresponds to the Hopfield model to obtain the ZHD, that is dry delay, and ZWD, that is wet delay. Okay, so HD is the polytropic layer thickness. By polytropic, I mean um, thermodynamic process with specific relation between thermal variables or thermal observables, that is rho Tp. These are not constant in the atmosphere, and up to which height these things are not constant or some relation is happening. This is known as polytropic layer. Okay, so isotropic, polytropic, you can understand the meaning. HD is a polytropic layer thickness or dry delay height, or dry, what you'll say, dry tropospheric height. Okay, and HW are the heights of dry and wet troposphere above the geoid. Okay, we are measuring it above the geoid, and height of the surface is the HS. So we are not measuring the characteristic heights from the height of the surface. We are measuring them above the geoid. We are using assumption inside this model that there is a constant lapse rate of temperature. So you have already seen how temperature is decreasing with altitude in the second slide, I think second or third slide, where we discussed about the troposphere, how that line was varying with the altitude. Okay, so that is the lapse rate is changing. The temperature has a lapse rate which is changing through different layers of the atmosphere. But here we are assuming that there is a constant lapse rate of temperature and a height integral which is linear function of pressure observed on the surface. So we are assuming linear function as well as constant lapse rate. So the assumption of constant temperature lapse rate is an important approximation that should be stressed. Means that this should not be assumed. Okay, that is why Hopfield model doesn't give a good approximation of the wet delay. All right, so the empirical constants K1, K2, and K3, you can see there are some studies like Smith and Winthrop, SN and Froome and Thayer. So these people have suggested, measured in their experiments and come up with the values of these constants, and these have been used inside the model. So ZHD, ZWD, and then we can arrive at the zenith total delay effective by multiplying these characteristic heights with the corresponding refractivity value. That is ND multiplied by, that is dry refractivity multiplied by dry characteristic height plus wet refractivity multiplied by wet characteristic height. Okay. So that assumption that we are talking of, this which should not be assumed very easily, this has been taken care as in the Sasta-Moanen model, which is more popular model generally used to compute the ZHD or the hydrostatic delay. Here, gravity is also not modeled with the dependence on the height. As we have seen in the Sasta-Moanen model, we are using the concept of hydrostatic equilibrium. Okay, we are computing pressure from the gravity measurements. Okay. So next is our Sasta-Moanen model. We've already seen that it requires only pressure, latitude, and height information to as inputs to compute the hydrostatic delay. Okay, there are few assumptions. Water vapor behaves as ideal gas. The whole amount of water vapor is in the troposphere. Water vapor pressure is described as the equation shown, and temperature decreases linearly with height. Okay, this is not a good assumption. Temperature doesn't increase linearly with height, but we have assumed it here and introduced the term alpha. Okay, alpha is the temperature lapse rate. So here we are not using a constant lapse rate. We are using which was the shortcoming of the Hopfield model. The gravity along the signal path is constant. These are few assumptions. So ZHD is obtained if Hs is the surface height of the geoid in meters, Ps is the surface pressure in m bar, and phi is the latitude of the station in degrees. So these are the inputs to the model. So Sasta-Moanen model, you can see the equations. ZHD equals to this. We have Ps, we have phi, and we have Hs as inputs. ZWD, the model provides a reasonable estimate of wet delay contribution when temperature Ts and water vapor pressure Es are measured at the site. So this requires a specific meteorological instrument to be there. Generally, in foreign countries where GPS networks are there, all the GPS stations in a network, they are combined with a meteorological sensor, and that is very beneficial for atmospheric and weather forecasting applications. Unfortunately, this is not so in India everywhere. We have very less networks. Currently, Survey of India is developing countrywide GPS network. So let's see that every station should contain met sensors so that we can get these kind of information and we can model the wet delay using these models. So the model provides a reasonable estimate if we have temperature and water vapor pressure. So inputs are temperature and water vapor pressure for calculating the ZWD. The input to ZHD are height, pressure, and latitude. The input to the wet delay are temperature and water pressure. I hope this is clear, easy to understand. You don't have to like remember all these equations every time. Tropospheric models like Sasta model, they claim to give detailed knowledge of height distribution. Which is they claim that this is not necessary to determine the refractivity integral. This makes the derivation of refraction formula simpler and they improve the accuracy of the derivation. But again, this assumption is not very good. We need good three-dimensional water vapor distribution according to height, and this is not contained in this model. Okay, that is why for determining the wet delays, these type of models are rarely used to predict. So this is because height is directly proportional to the ground pressure in a dry atmosphere. which is again, if I remind you, is the hydrostatic equilibrium phenomena. Now this model uses Snell's law. Snell's law, if you remember, the relation between different refractive index of two different mediums. Okay. Snell's law and gas law are used for getting the tropospheric delay. So this is the final equation for Shasta-Monin model for total tropospheric delay. We have seen ZHD, ZWD separately. Now this is the total one. I shall conclude today's lecture because this next slides would overload you for today. We'll continue this tomorrow. I hope everything is clear. If you have any doubts, I can entertain now. Or you can ask them tomorrow also if you encounter any doubts. I'll quickly show or glide through the slides in order to give you some memory about this lecture. Okay.
Ma'am, please upload this slide, ma'am, in Teams.
Yeah, I'll upload it. I'll upload after tomorrow's lecture. Okay.
Okay.
Okay. So these are the error sources we've discussed. On satellites, at receiver, and then during the propagation. Types of error in propagation, while propagation, that is tropospheric error and ionospheric error. Troposphere is electrically neutral and we have a temperature lapse rate varying like this. You can see that was what I was talking about. We can understand propagation basics from Maxwell equations. That is the origin of all this refractivity index and everything. Okay. From that, we derived wave equations. The red box below on the left hand side, these are the wave equations. Okay. And from this, we derive the equation for refractivity. The real part, it causes the refraction. Imaginary part causes the absorption of or the loss of the signal. Okay. Due to the dipole moment and very variable distribution of water vapor, it is very difficult to model. Okay, so we have two portions of refractivity, wet and dry. Wet means non-hydrostatic, dry means hydrostatic. So propagation delay is the difference between the longer actual ray path traveled minus the vacuum ray path if there was no atmosphere to influence the signal. Okay, that is capital G. So the difference between these two is the propagation delay that is represented by delta L. The tropospheric delays are affected, they vary according to different elevation angle. So we have two types of delays, that is slant delay with some elevation angle between 0 to 90 degrees and the delay at the 90-degree elevation angle, that is zenith delay. Okay. To compute zenith delay, we need mapping function. The zenith delay is further divided into hydrostatic and wet delays. ZHD depends upon pressure and location information. ZWD is more difficult to model, and we are introducing a term known as precipitable water vapor here. Okay, it depends on the mean temperature of the atmosphere. Mapping function depends, or we can associate mapping function with the elevation angle. Okay. Gradient information, gradient we can associate with the azimuth angle. Then tropospheric models, one is Hopfield model. It gives two characteristic heights, height of the wet atmosphere and height of the dry atmosphere. Monin model gives very accurately ZHT by inputting height, pressure, and latitude, and it gives ZWD by inputting temperature and water vapor pressure. Okay, I've summarized the whole lecture, so let's meet tomorrow. I hope there are no questions. Okay, let's leave.
Thank you.
Thank you, ma'am.
Thank you, ma'am.